Back to another video about vectors. Today's warm-up is a calculator active warm-up. It says the figure below shows the graphs of some polar curves. We see r equals 2 cosine of 3 theta and r equals 2. What is the sum of the areas of the shaded regions? So out of the two equations that we have this first one, r equals 2 cosine of 3 theta. We know that this is going to be the propellers or the petals, those three petals that are there. And then r equals 2, we know is just a circle centered at the origin with a radius of 2. So you could say this is kind of like the outer circle, and then the 2 cosine of 3 theta are the three propellers. So using your graphing calculator to help you out, would you be able to determine what the area of the shaded region is? And then choose one of the selected answers. So go ahead and pause the video, give everybody a chance to try it before I talk about the solution. All right, so hopefully you got a chance to try it. So first things first, kind of going over solution, the first thing that I would do is kind of come up with a game plan. If I was looking at this region that they were interested in, the shaded region, what I would say is maybe we can find the area of the whole entire circle. We know the entire circle has a radius of 2. So if the entire circle has a radius of 2, then we know that its area is going to be pi r squared. So then 2 squared is 4. The entire area is going to be 4 pi. So 4 pi would be as if we're talking about the entire circle. So then for our purposes, if we could find out what the area of one of these petals is, then we could multiply it by 3 and then subtract it away from 4 pi to find our final answer. So I think the natural petal or propeller to find the area of is this first one. So we know that it's going to start here at the points 2, 0. So I'd want to know when's the first time that it comes back to the origin. And if I can find that out, then maybe I could find out the restriction as to where this would fall in terms of its values of theta. And if I could find out what the area of one of these is, then I know the other two are symmetrical. I could just times it by 3. So looking at solution, that's exactly what I did. First found the area of the circle, which we already said is 4 pi. I took 2 cosine of 3 theta and set it equal to 0 over here. I divided both sides by 2, which didn't change the right side. I've asked myself where on the unit circle is cosine equal to 0 at pi over 2 and negative pi over 2. But because 3 theta was on the inside of cosine, you still divide everything by 3. So I got pi over 6 and negative pi over 6. So going back to my picture, you could say that on this top portion is going to go up to pi over 6, and bottom portion negative pi over 6. And that's actually going to complete this first propeller or first petal. So then how do I find the area in polar? Hopefully you still remember. It's just 1/2 times the values of theta upper and lower bounds times the r value or the radius squared. We know that r is 2 cosine of 3 theta. So that's why inside of here it's squared. The lower bound is negative pi over 6 and the upper bound is positive pi over 6. Took this into the calculator because it is a calculator type question and found the area of one petal to be 1.047. So then I multiplied it by 3 for all three petals, got 3.142. I took my area of the circle on the outside, 4 pi, subtracted the area of all the petals, and got 9.425, which was answer choice D. So I wanted to give you a chance to see another one of these questions in action so you could see how you're doing. Feel free to pause the video, chat about it, those things that we've been doing for the last several videos. Okay, so that being said, hopefully the last assignment on vectors went okay. I think we asked you to try 1 through 10, and there was an answer key. In case there wasn't, feel free to take pictures of these just to make sure everything was okay. I know that students in the past have said that's it, and they've kind of felt like weird that it goes really quickly and it should be harder, but no. Like I mentioned in the last video, vectors is kind of a nice topic to end the semester with. So I'm just going to keep scrolling through solutions if you didn't get a chance to see them. So if you want to pause the video, people snap pictures or talk about them, you're more than welcome to do so. Again, they were at the end of the last assignment. Similar for today's assignment, today will be, I think, 6 questions. I will have the answer key available as well, so you can double check things and make sure that it's going okay. I've noticed just small clerical mistakes in the past, so if you made a small clerical error, and it happens. If you see notation like this would mean using the calculator. In this case, you could say find a derivative and evaluate it at that t value on the bottom. So remember, your calculator also does integrals and it does derivatives in the program under the math menu. And then number 10 would look something like this. Okie dokie. So then the last section, we're still talking vectors and calculus. We talked about what is a vector. We know a vector has magnitude and it has direction. The magnitude will tell you how far to go, and the direction will tell you which way to go. So we did say that it was very similar to what we know about parametric. Let's take a derivative, just to find dy dx, take dy dt and divide it by dx dt, and that will give you the derivative. We do know the second derivative. You'd find it like normal and then divide by the original dx dt, just like we did in parametric. We know that dx dt is the rate at which the x-coordinate is changing, dy dt, the rate at which the y-coordinate is changing. I'm laughing a little bit because Watson came over with one of his toys, which is a Dunkin' Donuts coffee cup, and he was crumpling it, and he wanted me to take it and throw it. So I'm going to take it, and I'm going to throw it. So if you hear something in the background, that is Watson wanting to play. He doesn't realize that I'm recording you guys a video. Okay, so what else do we know? We know that the speed is the square root of each of the components squared and added together. We know that the arc length is the integral of that square root of the two components being squared and added together. So let's do it. The two questions that we have today are calculator type questions. So the first one comes from 2003. It says, and it's one of the last questions in the multiple choice in 2003, which is a long time ago, but the questions are similar in terms of repeating every now and then. A particle moves along the x-axis so that any time t greater than 0, its acceleration is given by this equation. If the velocity of the particle is 2 at time t equals 1, then the velocity of the particle at time t equals 2 is blank. So a couple things stick out. We know that we have the acceleration, which is like the second derivative. We know that if we go backwards, if we find the antiderivative or integrate, it will take us back to velocity. And if we integrate one more time, it will take us back to position. We do know the velocity of the particle is 2 at time t equals 1. And then we're going to try to find out what is the velocity of the particle at time t equals 2. So notice that this part is kind of like telling us what's happening at 1. This would kind of be like an initial condition. And then we're trying to find out what's the velocity of the particle at 1 time unit after that. So what I would do is say, okay, if I have acceleration as the natural log of the quantity 1 plus 2 to the t, and I want to get to velocity, I'm going to need to integrate. So maybe my notation would look something like this. I would say to find the velocity, I need to integrate. Or would be a logical place to start the integral? Well, we know the velocity of the particle is 2 at time t equals 1. So then t equals 1 can go on the bottom. We do want to stop the integral when t is equal to 2. So 2 is going to go on top of my integral. What are we going to integrate? We're going to integrate the natural log of the quantity 1 plus 2 to the t. And of course, with respect to t. So now this integral is going to tell me how the velocity is changed from 1 to 2. But then since I do have that initial condition, I know that the velocity of the particle is 2 at time t equals 1. Then I'm going to take what I know about the change in the velocity from 1 to 2, and I'm going to add that positive 2. Now the reason why we're adding is because we're at position 2, and then we're saying, and that position or velocity is 2 at time t equals 1. We then found out from the integral, this first part that we wrote, how it changed from time t equals 1 to t equals 2. So we're going to add it to its initial condition. In the case that we were trying to do this for a time value that was, let's say, more than t equals 2. Let's say that we knew the velocity of the particle is 2 at time t equals 3, and we were trying to find out what's happening at time t equals 2. Then we would integrate from 2 to 3 and then subtract it away from the initial condition that we know. So this is actually one of the last kind of big hints or big points to make about stuff like this, is that in the case that you're trying to go backwards in time, then you'll subtract. In the case that you're trying to go forwards in time, then you're going to add. So in this case, since we knew t equals 1 and we were trying to find out t equals 2, we integrated from 1 to 2 and then added it to that initial condition. Now at this point, this can go into your calculator. So if you take this into your calculator, you can find out what this integral is going to be. So feel free to pause the video if you want to do that, or maybe you've already done it. So when I did in my calculator, I got 1.346 for the integral, and then if I added 2, I got to an answer of approximately 3.346, which for our purposes is going to be answer E. So in our first example here, multiple choice, answer is E, and there are a couple key points that were made. All right, feel free to pause the video if you want, or chat together. All right, we only have one other example today, but it does have 4 parts. It is a calculator question, and it's a good one. So let's see if we can do it. So it says an object moving along a curve in the xy plane has the position x, t, y of t at time t with dx dt equal to sine of t cubed, dy dt cosine of t squared. At time t equals 2, the object is at position 1, 4. So we know the position is going to be 1, 4. That's something that's good to know. And we do know dx dt and dy dt. So in this case, we could say that this is the velocity vector. So if we wanted to write it as a vector, maybe we could do it right here. We could say the velocity. And then as a vector, we know we can use our angled brackets. The x component sine of t cubed and the y component cosine of t squared. So if you wanted to, right there. So here it says, can we find the acceleration vector for the particle at time t equals 2? Well, we definitely can. And remember that it is a calculator type question. So we do know the graphing calculator has the program to find derivatives. So if you go into your calculator menu for math, you'll see that there is a program called nderive. So we can actually do it for both components. And the nice part about nderive, we can even tell the calculator where to evaluate. We want to evaluate it at time values of t equals 2. Now when you go use nderive, it's going to have the variable in terms of x, but it's not a big deal. We can actually treat x like t in this case and find out what it's going to be. So if you want, feel free in your calculator to try it out. We're going to have to do it for the x component, so we need the derivative of this guy, and we're also going to need the derivative of this guy. So it's not too bad. You could even do it without a calculator if you wanted, but since they're going to give us the calculator as an option, we know that we could do it. In terms of an answer, for the x components, what I got for the acceleration at time t equals 2, I got negative 1.746. For the y components, acceleration of the y component at time t equals 2, I got 3.027. So if you want to pause the video just to make sure everybody can get that, I believe that this is the answer for part A. All right, and there's your answer for part A. Let's talk about part B. So same situation. Can we write the equation of the tangent line to the curve at the point where t is equal to 2? So we want to find out where t is equal to 2. What is the equation of the tangent line? We've written the equation of a tangent line many times this year, so we know we're going to write it in point-slope form. So in order to write something point-slope, we're going to need some points and some slope. So since we're writing the equation of a tangent line to the curve, we'd like to know about the position. That would kind of tell us like the x1, y1. So we have that. So that's going to be the first part that we're going to need. So this will be your x and your y. So first things first, I would have y minus 4 is equal to the slope, which we don't know yet, and then x minus 1. So really the only other thing that we need to go find in terms of conversation is to find out what the slope is. So hopefully you'd agree, after sitting in a calculus class for several months, slope translates to the derivative. We know that the derivative in vectors is very similar to what it was in parametric. So we know to find dy dx, we need to take the derivative of the y components and divide it by the derivative of the x components. We do know that dy dt is cosine of t squared. We do know that the derivative of the x component is sine of t cubed. So our derivative would look something like this. But we do know that we're doing things at the t value of t is equal to 2. So if I was to plug that in, cosine of 2 squared is the cosine of 4. Sine of 2 cubed is the sine of 8. We can take this into the calculator, and you'd get something like negative 0.661 with the rounding. So then this is going to be our slope. This is going to be the derivative at t equals 2. So then to put down a final answer, we still have the y minus 4 equals. We're going to steal the slope that we just found, negative 0.661, and then times it by the quantity of x minus 1. So I'm thinking a final answer for part B. The equation of a tangent line is going to look something like y minus 4 is equal to negative 0.661 times the quantity of x minus 1. I don't mean to be repetitive, but feel free to pause the video if somebody wants to take a look at it, chat about it, or take a picture. Hopefully I'm not going too fast. Again, we've written the equation of a tangent line many times. So again, it's an old topic with a new twist. We're just doing it for vectors. Okay, I'm going to keep rolling. How about part C? So same situation, part C says, can we find the speed of a vector at t equals 2? So any takers, do you know how to find the speed of a vector? Do you know the difference between speed and velocity? Well, of course, speed does not have a direction and velocity does. So in terms of vectors, we know that in order to find speed, you'll just have to take the big old square roots of the derivative of each component squared and add it together. So this was the last conversation that we had on the last video. Speed will look something like this. So then for our purposes, we are still doing it at t equals 2. So I think we're going to have a big old square roots. We're going to have dx dt, but evaluated at 2. So if I go up to dx dt, it's sine of t cubed. 2 cubed is 8, so we're going to have the sine of 8. And that is going to be squared. And then we're going to add it to dy dt at t equals 2. So dy dt is cosine of t squared. So 2 squared is 4. So we'll have the cosine of 4. And then we'll square this quantity as well. If you take this into your calculator, I got approximately 1.186. So not too bad. Again, just tying it into the last conversation. All right, so that one's not too bad at all. Part C, just finding the speed. So the last one we have is find the position of the particle at time t equals 1. So as we mentioned, we do have the velocity. So if we have the velocity that's here, then how can we get to position? Well, we want to find it at t equals 1. Some people would say, well, don't we already know the position? Don't we already know the position is at 1, 4? So anybody know why that wouldn't be the right answer? Well, that's going to be the position at time t equals 2. And we're trying to find out what is the position at time t equals 1. So notice we're trying to go back in time. So if I know the position, the x component is 1 and the y component is 4, when time is equal to 2, then how can I find the position when time is equal to 1? Well, if I start with this velocity, I can go backwards to position by integrating, but then would I add or subtract this initial condition? In this case, we're going to subtract. Because I'm going backwards in time, I knew this for t equals 2, that this was my position. I'm trying to find out what's happening at t equals 1. I'm going to subtract it away from this initial condition. But what about right here? If we were trying to find out what is the position of the particle at time t equals 5, then would you add or subtract? Well, if it was t equals 5, then I would add because I'm trying to find the position at a time value that happens after the initial condition. But in this case, since I'm trying to find the position of a particle at a time that's happening before the initial condition, then I'm going to subtract. So I have to do it kind of in two pieces. I've got to do something for x and I've got to do something for y. So how about for position? What if we say that position can be written as this guy right here, right? X of t and y of t. So maybe we'll start with the x component. We'll say x of t is equal to, and in this case we can say, well, what do we know? We know the initial condition. The x components at t equals 2 has a position of 1. So I can start with 1, and then I'm going to subtract away the integral. Well, then since I know what's happening at t equals 2, and I'm trying to find out what's happening at 1, that kind of tells me the bounds. It's going to go from 1 to 2 for the x components, which we know dx dt is sine of t cubed, and then dt. We can take this into the calculator just as is, so I'll give you a second to do it. Again, you can pause the video if you'd like. And what I got on my calculator was 0.782 for the x component. Now we can do the same thing for the y components. So then I'm going to set up a y of t. And then we know that y of t at time t equals 2, the y component has a position of 4. And since we are going back in time, we're going to subtract. Again, the integral is going to go from 1 to 2 since we know what's happening at 2. That's the initial condition. We're trying to find out what's happening at 1. So we're trying to find out what's happening in the terms of difference of the position of the y component from 1 to 2. We know that dy dt is written as cosine of t squared. And then it's in terms of t. So we can also take this guy into the graphing calculator. Give you a second to do it if you want to pause. And then on my calculator, I got 4.443. So in this case, it very much resembles what we did in example number 1. And that was kind of the reason why I wanted to do it in example number one, just to kind of give you an idea of what both situations look like. In the case that you're trying to predict what's happening at a time later than the initial condition, then of course you can add it. I know I mentioned that, and sorry if I sound repetitive, but I want to say one more time, if you're trying to find out what's happening for position at a time before the one that you know in the initial condition, then you're going to have to subtract. So in this case, if we wanted to say what is the final answer, what is the position at t equals 1, we could write it as a point. We could say it's 0.782 for the x component and 4.443 for the y component. So in this case, this will be my final answer. So we'll throw a couple stars around it and say this is going to be my final answer. Okay, so only 2 examples here for vectors on the day 2 video. So then if you go to the back of this paper, there will be a couple questions back there. So since this is our second practice set, if we could try 1 through 6, and there was going to be an answer key available if you want to double check your work as you go. So if you can try all 6, and I believe on there it will actually tell you which questions you are allowed to calculate and which questions you're not. So please try to do the questions as it says. All of these questions are previous AP questions. I know they're not in like AP format, but they are going to give you an idea of what the questions would look like on the AP exam. And just like that, we're getting very close to the end of the material. And then we'll try to give you guys a full-length practice test so you can see what that looks like. You can score yourself, kind of see where you stand, and you still have a couple weeks to prepare. Any time that you have still available, I'll encourage you to go into your practice workbook and kind of work through it. I am going to try to post some solutions. If you want some solutions ahead of time, just shoot me an email and let me know about the practice workbook. Otherwise, now it's kind of getting to that point where it's kind of crunch time. So that cheat sheet that I gave you guys would be a good thing to start committing to memory. Some of the unit circle stuff, trying to practice that, listing off some of the big points of unit circle just so you know them, kind of going into it. And then, of course, some of the review we're going to do is going to help as well. All right, guys, if you have any questions, feel free to reach out or write it on the shared doc, and I will try to answer those questions as soon as I can. All right, I hope you guys have a great rest of your day, and I'll catch you in the next one. Adios!